Alright, so in this video we're going to do a quick review on graphing. So, whenever we are graphing something, we want to make sure we do the following. So, make sure you give it a title. Make sure you label the axes with units. Make sure you use the available space effectively. So it shouldn't be a small, tiny graph for a large area. Make sure you use sensible scale. So your axes should go up in increments. So maybe 10s, 50s, 100s, 0.5, whatever makes sense for your data. Make sure you plot all the points correctly, and then you should draw a line of best fit. You are not going to be connecting the dots in a line like this. You're not doing that. You're going to be doing a line that goes through most of the dots that shows the trend of the data, not this. And then if you have dots above and below the line that don't necessarily fit the trend, you might want to look at those. Alright, so best fit graphs. This is what we typically use in chemistry. So your best fit line should pass as many points as possible. It should touch as many as possible, but you'll have some that are not necessarily going to be right on that line. Now, if you are reading a graph, so if you're trying to get information on the graph, and let's say that your data stops at 50 millimeters or milliliters, but you're looking at, you want to know something about 75. So here is where it is, but all your data stops here. Well, if we want to, we can extend this line and to get information about this particular point, but this is called extrapolation. So when we do this, the extension of the data, that's extrapolation. Now, if we're just looking for information on a particular area, so maybe it's on the line, that's called interpolation. Make sure you know the difference. All right, so a slope. If we are looking for a slope, which is also called gradient, slopes can be very useful because it can tell us a lot of different things. We often look at slopes when we're looking for a constant value, because if we get a straight line, that is a constant value because the slope is the same throughout the line. So if we have something like this, or this even, those will have slopes that are constant. So the equation for a straight line is y equals mx plus b, where x is going to be whatever your independent variable is, y is your dependent variable, c is going to be the intercept on the x-axis, or the vertical axis, I'm sorry, the y-axis, and then this is our slope. So if we have a straight line, we can get this equation that goes with that straight line, and we can get a lot of information about that, or about different points on the graph, including the slope, or a value for x or a value for y. Now, finding the slope, that's going to be the rise over run. If you're looking for a particular point on a graph, so let's say that we have this, and then I want to know what the slope is at this particular point, I would get the tangent line, so the line that just skirts up at that point. So it's still going to be rise over run, so how much does this line go up versus how much does it go over? Now, your axes of your graph, your x-axis should be the independent variable, so it's whatever you are changing in your experiment. The y-axis should be the dependent variable, so what are you measuring in response to whatever you changed throughout your experiment? Now, we have two different types of errors that we're going to be looking at when we look at a graph. We have systematic and we have random. And you can actually recognize these types of errors based on your data and in the graph. If you have outliers, okay, outliers do suggest that some of the data is not reliable. A systematic error produces a displaced straight line, so it will give you the same type of error throughout the experiment. So it will maybe make your density a little bit higher each time or a little bit lower each time. So it just changes where the line should actually be random uncertainties are going to be the points that are not quite on the line. They're above or below. So let me show you what I'm looking at. So let's say the perfect results are right here with the black line with the circles, okay? Now, if we have a systematic error, maybe the line is shifted up, or it could be shifted down, okay? That would be the sign for a systematic error. We're getting the same trend, but it's moved up slightly more, or it could be down. Now, random errors, you can see based right here, okay? So this is not quite touching the line, and then that is a result of a random error. All right, now with our data, we can use graphs to manipulate your data. So if you have an inversely proportional relationship between the two variables, you're going to get a line that looks something like this. As one goes up, the other one goes down. But if you have that inverse relationship, you can manipulate this data to get a straight line by simply taking the values that you have on your x-axis and getting the inverse of those. So we're going to take all the x values of our data points and we're going to do 1 over that value. So if your point is at point, let's say, like 100 here. So if the x value is 100, now that new x value is going to be 1 over 100. Same thing here, 150. The new value of that the x value will be 1 over 150. And then we're going to regraph it, and then we're going to get a straight line. Why do we want this straight line? Because then if we have this, that means our slope is constant. So we can find whatever the constant is in this experiment. We could also use that to make a trend line equation. Now, calibration curve, this is something you guys have done before. This is something that we do a lot in chemistry. So basically with a calibration curve, you are measuring some amount where you know the concentration, or you know usually it's a concentration versus like something else. So we could do concentration versus the amount of absorbance with a spectrophotometer. We could do the concentration versus the density. We could do the concentration versus the specific heat capacity, and then graph all that information. What we do then is we will generate a graph which could look like this. Let's say that we're looking at concentration versus absorbance. So if I were to take an unknown solution where I don't know the concentration, but then I can go and actually just measure the absorbance, and then I get the absorbance and it's about here, then I can figure out, okay, what is the concentration? And usually we do this with that trend line. We will go get the equation of the straight line, and then we can use that equation to determine an x value or determine a y value, depending on what you're doing. All right, so this is just a basic review on graphing. A lot of this you've probably already seen before.